iPad. I'll just kind of stick to the paper. That's probably much better. Yeah, so here is an integral of 1 over 2t squared plus 3t plus 1. And immediately the things you got to recognize with these types of problems is notice that the bottom has a quadratic. So we actually can simplify this by factoring. And I think from there, oh, dx, yeah, disrespect to t. You're right, you're right. I'm just so used to putting the x. Have it. Yeah, so I think partial fraction decomposition. So the one thing you just got to kind of notice that if we can factor out the bottom, then we are good to go. So the way we factor this and the way I like to do it is I typically multiply the 2 times 1, which gives me a 2. And I want to find two numbers that multiply to 2 and add to 3. Again, this is super simple. Everyone kind of knows that this is going to be 2 and 1. So then the bottom turns into 2t squared plus 2t plus t plus 1. And this is how some people like to factor it. And then from here, we kind of do a grouping where you factor out a 2t. Gives me a t plus 1. And then in this second group, you factor out a 1. So t plus 1. And when you're factoring in, you kind of want both of these to be the same value. So you just want 2t plus 1 times t plus 1. Not bad. And that basically turns our integral into what we want, right? Now we get integral of 1 over 2t plus 1 times t plus 1 with some disrespect to t. Okay, so now we're ready for the partial fraction decomposition. Because again, once you can factor this out, then the idea is that you're going to rewrite this into a sum of rational functions. So we have the integral of a over 2t plus 1 plus b over t plus 1. Now, why am I doing just a and just b? Well, on the bottom, notice that we have a linear factor. Let me just kind of move this away from my vicinity. I don't like the way it feels. Anyway, yeah, the reason why we have linear factors is because, or the reason why we have a and b is because we simply have linear factors. Think of it like this is degree 1. So then on the top you want 1 degree less. So your degree 0 is just a constant. So if you were to get common denominators, this is the idea. I'm kind of working everything through. I will multiply t plus 1 to the top and bottom, and I will multiply 2t plus 1 and 2t plus 1 here on the top and bottom. Because the idea is that just focusing on the numerators, we have a times t plus 1 plus b times 2t plus 1, and this is supposed to equal the numerator that we have on here. Hello, Goat Dory? Hey, from Chicago. How's everyone doing in Chicago? I just had my trainer who was in Chicago for the St. Patrick's Day parade. And then she went to the Trump Tower for buffet. That was wild. Anyway, we go here. I like to use the cover-up method, or actually I'm going to show you a different method. If we factor out the a into both of these, we get at plus a. And if we factor out the b into both of these, we get 2bt plus 2b. This is a method that a lot of students do because you group the values that have just a t, and that's a plus 2b, and then you group the values that don't have a t. And this is not a 2b, this is just a b. So then you have a plus b is equal to 1. Okay, so the idea, there's a t right here. This is a constant because there's no variable. This is the coefficient in front of the t. So if you were to match it to the right-hand side, this coefficient right here needs to be 0 because there's no t on the right-hand side. So a plus 2b has to be 0. So we can basically say a is equal to negative 2b, and we'll use that in a second. And then here we can say that a plus b has to be equal to 1 because that's the constant, and it needs to equal the constant on the right-hand side. So now that we know that a is equal to negative 2b, we can bring this to the other side. Guys, am I doing something wrong here? This should be a plus b. Why do I feel like I'm doing something wrong here? But I don't know. If I get anything wrong, let me know. So I get negative 2b plus b is equal to 1. Then this right here is negative b is equal to 1, so b is equal to negative 1. Okay, we're going to use that in a second. Plug this negative 1 back into here, then we'll get that a is equal to 2. So we found the values. We found the value of a, we found the value of b, so we're going to plug that in here, or up here. So we have integral of the a value, which is 2 over 2t plus 1 dt, and then the b is -1, so negative integral of 1 over t plus 1 dt. Okay, from here I trust that you can do u substitution. I'm hoping that at this point, I mean, if we're doing partial fraction decomposition, you could do that. So this will equal to the natural log absolute value of 2t plus 1 minus the natural log of the absolute value of t plus 1, and let's not forget our plus cheese. And then for extra credit, I guess we can just use properties of logarithms and do natural log 2t plus 1 over t plus 1. We have our plus cheese, and then we're done. We are done. Yeah. This is something I even mentioned in a book of integrals. I talk about PFD. That's literally in chapter, what chapter is this? Chapter this is page 47. 47, it's like the 6th chapter, something like that. Yeah, super useful. Okay, so how about we go to the next problem? I'm writing on a simple, honestly, I just got this from Amazon. It's like a black sketch pad. Yeah, and I'm just using like acrylic pens that I just bought on Amazon. And then this is book of integrals. Here is book of marvelous integrals. I wrote these. I'm working on another book called Book of Evil Scribbles that hopefully I'll get done by summer. But yeah, if you want to practice your integration techniques, you can do that. All right, let's go to the next problem. Yeah, partial fractions are a pain sometimes, you know? One mistake and you're basically done. I think you can use it for Calc 2. I mean, honestly, Calc 2, this is basically a lot of students in Calc 2, I'll give you the table of contents, like exponents, just regular stuff, u-sub, special trig integrals, long division. The pun integral is just like partial fraction decomposition, ultraviolet voodoo, which is integration by parts. And then we have like some interesting like integration. So you basically stop here, like power reducing integrals. So yeah, I think it's super helpful. Okay, next problem. I'm sure a lot of you guys are gonna already tell me what the answer to this is. This one's too easy, guys. And again, I just pulled these out. A student was covering these, needed help not too long ago, and I decided why not, you know, just do it together, right? So what do you guys think? What do we use on this one? It's basically gonna be a simple u-sub. U-sub, that's it. Nothing fancy, nothing crazy about that. Yeah, simple u-sub. And immediately the way you recognize it, I mean, you see the natural log of x and you just think right away, the derivative of natural log of x is just 1 over x. So it seems like this will be perfect because u is equal to the natural log of x. du is 1 over x dx. What I like to, or I prefer to do, is move the x to the other side. X du is equal to our dx. And this is exactly what we're going to use for our differential right there. Okay? So then we go to integral sine of, we have our u value. I don't like to immediately get rid of the x. I get rid of it when I plug in this value x du in for the x. So we get x du, and haha, boom, x's cancel out. So leaving us with an integral of sine of u du. And this is something that a lot of people do. Yeah, so we're going to do tricks of Freleng functions. You have to give me an example of that. But yeah, here we are, guys. We integrate sine of u, and that's going to be negative. Wait, no, it's going to be Bro, I always forget the integral. This is going to be negative cosine of u plus your cheese, guys. But then don't forget the u value was the natural log of x, so we get negative cosine of natural log of x plus your cheese. Does everyone get mixed up? I mean, the derivative of sine of x is cosine of x, but I always get it mixed up when I try to do the integral of that. I don't know why. I always get, it's like a little hiccup right there. Not bad, not bad. Again, you can definitely practice these types of problems in Book of Integrals. Book of Marvelous Integrals has more like complex things. So like for Calc 2, there's improper integrals, there's like double integrals, the Gaussian integral Feynman technique. There's like all these like nice little tricks to it. And then you do like contour integration, just kind of fun. All right, let's go to the next one. I think there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 problems, so hopefully we can get through all of them. I think we will. So integral from 0 to 1 of, let's do arc tangent of x over, whoa, where is this? Oh, this is the square root of arctangent of x, I'm sorry, of 1 plus x squared dx. Give you a second to kind of think about it. 6, 7. Let me know what you guys think we can use for this. U-sub. For some reason, I've had 2 students in different occasions, different classes, literally different states, who covered this particular problem, which is pretty crazy. Use theta. No freaking way that you want to use theta. That'd be insane. I mean, I guess we could do it, but we're gonna use the u-sub. Someone already got the answer. But go, Tawdry. I hope I got your name right. I'm so sorry. You have to use your bounds. Don't forget that. But we're gonna use u is equal to the arctan. And again, what kind of gives that away? Well, I have the 1 plus x squared on the bottom, and I know that the derivative of arctan is 1 over 1 plus x squared, so I think that's what I want to use. So our du is 1 over 1 plus x squared. There it is, dx. So we're going to use this for our differential, but first let's do 1 plus x squared du. Again, I just like to multiply it to the other side. It just satisfies me. Guys, don't forget, you have free will. You can integrate how you want. You can literally write it out how you want all the time. Okay, so our bounds. So when x is equal to 0, that's the lower bound. We're going to plug in 0 in for here. U is equal to the arctangent of 0, and that's just 0. And then when x is equal to 1, u is equal to the tan inverse of 1. You can't forget this one. It's pi over 4. So now we have our new integral, our new bounds, and new integral. 0 to pi over 4 of square root of u. Maybe I can just already write it as u to the 1/2, because I know I'm going to have to use that. Of over 1 plus x squared times 1 plus x squared du. And once again, these things cancel out. That's nice. Okay, so we're left with just integrating u to the power of 1/2, which gives me u to the 3/2 divided by 3/2, which is just multiplied by 2/3, but we still need to implement the first fundamental theorem of calculus. So we need to plug in the pi over 4. We get 2/3 pi over 4 to the power of 3/2 minus, and then you plug in your 0, and that's just going to be 0. So if you take the square root of 4, guys, don't forget 4 to the 3/2 is equivalent to square root of 4 to the power of 3. So square root of 4 is 2 to the power of 3. That's going to be 8. So on the bottom, we really have 8. So we have 2 over 3 times. This will become pi root pi over 8. So then, is it going to fit? 3 pi root pi. Oh, not the 3, sorry. It all canceled out. It's just over 3 times 4, so that's going to be 12. Oh, this is what happens when I got a little crazy. So anyway, 2 over 8 just becomes 1 on the top, 4 on the bottom, and then you multiply those, you get 12. Yeah, you got to be super careful, especially with your work here. Look at that. So far, we've done 1, 2, 3 problems. Not bad. We should use a different color pen. Now we're going to use orange. You think I'm going too fast? Okay, I'll be a little slower. I'm sorry. I thought I was going super slow. Elliptic integration, maybe for another time. Right now, again, what I'm doing, for those people that are just like tuning in, I'm basically doing problems that a student of mine was just covering not too long ago, and I just thought it'll be nice to kind of, you know, just like anyone that needs to practice, that's what we're doing. This black book, I just got it on Amazon. It's black sketchpad. You can actually go on the link in my bio, and then if you go to my chirp page, there is a link all the way down that says like my gear, and you'll find it there. Yeah, it's really fun. To be honest, I've been kind of experimenting with these pens and these pencils, and then the papers. Yeah, super satisfying, to be honest. Okay. I don't watch UFC, no. I've watched it before, but, you know, I don't have time, I guess you can say. Guarantee you won't guess what method I'm going to use. If you do, that's crazy. Yeah, someone was asking... oh, why did we change bounds? Just to kind of go back. So the integral here is in terms of x. When we turn it in terms of u, you're kind of going to a new universe, if you will. This is something that Black Pen, Red Pen said, like we are in the u universe. So our bounds have to change with that, because if we leave it from 0 to 1, we're going to have an integral from 0 to 1 of u to the 1/2 du. And that is not the same. This will not give us the same value because the zeros and ones were for the integral, but they were in terms of x. And because we made a substitution, we said u is equal to the arctangent of x. So we have to account for that. It's a little hard to, again, I can maybe make a video about all those things. But I should make a video. I keep forgetting that, you know, the basics are always going important. All right, am I going to split the integral and then use partial fractions? That's basically, I mean, I guess I'll use partial fractions. I don't want to confuse a lot of you guys. But I'll use a nice method. I'm going to use, can I use it here? I guess I could use it. I'm going to use it some other time. But I was going to use something called Scribble's lemma. But so let's go ahead and do partial fraction decomposition, because that's basically the type of stuff that people use. So same idea. If you look at the bottom, and if you can factor it out, you should definitely go with that. That'll give you some more information and maybe some ideas as to what you can do. So if you notice, I just factor out an x from the bottom. So I have x times x plus 2. Okay? So I'm going to use Scribble's lemma on this one. All right? I'm going to show you guys how to do this. So the idea, if I were to use partial fraction decomposition, this will be an integral of a over x plus b over x plus 2. Now, why just a? Why not ax plus b or bx plus c and so on? I studied at UC San Diego, by the way, mathematics. So the reason why is because here I have a degree of 1. So on the top, I need to have 1 degree less. So if this is degree 1, then this one needs to be degree 0. In other words, just a constant. But I'm going to show you Scribble's lemma real quick. So I want you to look at the bottom here. I label this as f of x is equal to x minus 1, so that's top function, and g of x is equal to x times x plus 2. Now, luckily for us, we know g of x is also x squared plus 2x. So I want you to keep in mind our derivative is 2x plus 2. And the reason why I'm doing that is because a is actually equal to f of 0 over g prime of 0. Now, why 0? Because 0 is the value that makes it discontinuous. Okay? So if you were to plug in 0 into your f of x, you would get 0 minus 1, so negative 1, over g prime of 0. So plug in 0 in here, so 2 times 0 plus 2. So that's just 2. I found my a value. And b is equal to f of, what makes this bottom equal to 0? Negative 2. So f of negative 2 over g prime of negative 2. Again, I wouldn't use this in a calculus, like in your calculus exam. I would definitely go through the motions of like the cover-up method and finding all these values. This is just a nice little shortcut, especially when you have linear terms. So then f of negative 2, plug it in here. Negative 2 minus 1, that's going to be negative 3 over, and then this will be negative 2, or I'm sorry, negative 4 plus 2, so negative 2, so 3/2. And hopefully these will be the correct answers. Let's try it out. The idea is that this will be integral of, what do we get for a? Negative 1/2 over x, and then plus 3/2 over x plus 2. And I'm hoping that will be correct. Let's see, if we multiply the 2, if we get common denominators, this will be negative 1/2 times x plus 2 plus, and then multiply the 3/2 by x. And then what do we get? Negative 1/2 x plus or minus 1 plus 3/2 x. Add these together, the common terms. That's 2 over 2, so just x minus 1. Hey, that's the correct numerator. It's a cool little trick. By the way, I have this in Book of Marvelous Integrals, and I talk about this in here, Scribble's lemma. Scribble's lemma, page 56. So if we go here to 56, it's all right here. There's like a nice explanation of it. Will highly suggest or recommend that you can mess around with it. Again, this is something that I never found it online, so that's what I named it, Scribble's lemma, after Math Scribbles. I know it's not a lemma, but yeah, that's basically what it is. So we have our a and b terms. So we just need to integrate this. Guys, this just becomes a simple integral or a natural log integral. This will be negative 1/2 natural log absolute value of x plus 3/2 natural log of x plus 2 plus your cheese. But again, would not recommend using this during the test. Definitely do all the work on your end. When did I write this? So Book of Integrals was written like 2 years ago, or like a year ago, I would say. Coming on 2 years. This one I wrote last June. And I'm coming up with another one called Book of Evil Scribbles that hopefully will be sort of fun to do. An integral, everything in life is explained by an integral. The area underneath the curve is the sum of infinitely many things. We can go into all that later on. I feel like, you know, going live is just good because we get to chat with y'all. I'm going to answer some questions because someone said, I'm a 9th grader. The most complex all we can do is partial differential equation. Julian, bro, you're an animal. You're an animal. Partial differential equations? Dude, that's a flex. That is the flex you think it is. Okay, so we have x secant x tan x. Sorry, I'm just bringing down my tripod here so we can do that. What do you guys think? What should we use? Integration by parts, IBP? Or will someone call it something else? By part? Is anyone going to call it something different? U-sub? Okay. Okay. Integrate, technically, yes. I'm looking for the best name for this method. DI method, technically, yes. But there's voodoo, ultraviolet voodoo. Let's go. Now, the idea is just integration by parts. You can call it whatever you want, but we're going to use UV minus integral V du, because that's what's going to require for us to use. We need to use integration by parts. Why? Well, if you go down the list and you try to do like U sub, if u is equal to secant x tan x, then we can't find the derivative for that. If u is equal to x, then du is dx, but then we're still left with the secant x tan x. So integration by parts is really helpful when you have like a combination of like trig functions and you have an algebraic function here. Una vaca vestida en uniforme. That's right. That's right, Rodrigo. That's exactly what it is. In fact, I do say that in the Spanish version. I call this ultraviolet voodoo, but I say una vaca vestida de uniforme. Okay, so how does this work? All right. Well, we got to find a value for u, and typically the u term is something that you can easily integrate. There's like a method to these. It's called ilate or liate. Some people do that. Oh my gosh, limit comparison test. Okay, I'll do that in a second. Give me 1 second on limit comparison test. Okay. Okay. Let me just finish this and I'll talk about limit comparison test because that's something that a lot of people are trying to do in Maryland. So u is equal to your x, du is equal to your dx. So your dv is the other term, the remaining stuff, which is the secant x tan x dx. Secant x tan x dx. And v is equal to the integral of that. And that's just secant, guys, because the derivative of that is just going to be secant. Yep. Sorry. Okay, so let's continue. UV minus V du, ultraviolet voodoo. That's the way I like to remember it. So we do UV, so x secant x, okay, minus integral of V du. So V secant x, and then du, which is my dx. Guys, you guys never saw that. All right, so we have x secant x minus the integral of this. It is your lucky day, guys. A lot of people know the answer to this, but it is your lucky day. I'm going to show you. Marilyn wants to do a limit comparison test, and we're going to do that in a second. But just imagine, like if I was to multiply secant x tan x into both the term on the top and bottom. So this will turn into integral of, if I distribute the secant into both of these, secant times secant, secant squared x, secant times tangent, plus secant x tangent x over secant x plus tan x. But guys, look, if I make my u equal to secant x tan x or secant x plus tan x, I'm sorry, my du is the derivative of secant x, which is secant x tan x, plus the derivative of tangent x, which is secant squared x dx. Well, that's all up here. This is my du. So what you have is you have the integral of 1 over u du, which is just the natural log of u. Well, the natural log of u, since u is secant x tan x, that's what the integral of secant x is. It is natural log of secant x plus tan x. And let's not forget our plus cheese. And we are done. And we are done, guys. Okay. So I want to definitely do very quickly. And again, Marilyn, there's so many questions that we can do with limit comparison test, but someone was asking about limit comparison test. And it's actually pretty exciting because someone was just going over that. So the idea is that if you have a series n is equal to 1, and let's just say you have like 4n squared plus 3 over 6n cubed plus 1. And we want to ask whether this converges or diverges. Now remember, converges means that it just adds up to a specific value. I don't live in Cali, I live in Washington. I used to live in Cali, in OC. Okay? So converges means that it adds up to a specific value. Diverges means that it adds up to infinity. Okay? Big Bong, I'll answer your question in a second. Okay? So the way this works, if we're going to use limit comparison test, some people, what they like to do is they like to already see that the bottom has a degree of 3, the top has a degree of 2. So we need to think about a specific value that we want to compare it to, and we want that value to match the same degree on the bottom. So we need another degree here. In other words, we're going to compare it to 1 over n. Because this is degree 1, that's degree 2. If you combine the two, it will be degree 3. I'll show why in a second. Other ways that some people like to do is they get rid of like all the noise in here, okay? Just imagine you got rid of the 3, you got rid of the 1, you get rid of the 4, you get rid of the 6. You're left with n squared over n cubed, which simplifies to 1 over n. And that's the series that I found, okay? So a lot of people already say that, okay, this is exactly... a lot of people, again, the way I see it is I see degree 3, this is degree 2. I need a degree 1 that I'm going to compare it to. Limit comparison typically works this way. Or you can get rid of all the noise and you have 1 over n. So this is a series that we're going to compare it to. Now, this is our harmonic series, or some people can say this diverges by p series. And it's important for us to know that. If we're going to compare it to something, we have to know what it does. So this diverges by p series, which if you're in Calc 2, you should be able to prove now. And I do mention this in Book of Marvelous Integrals. I always ask you to have it converge. Okay? So now that we have that, we're going to do the limit comparison. So LCT, limit comparison test, tells you that if the limit as n approaches infinity of a sub n over b sub n is greater than 0, and the series that we're comparing it to, b sub n, in this case diverges, or whatever it does, if it diverges or converges, then the series that we're focused on, or the series in question, will do the same. Okay? That's what limit comparison test does. And it's really beautiful. These are like super easy to do, because now what you do is you take the limit as n approaches infinity of our a sub n term, and our a sub n term is the original one. So think of it as 4n squared, squared plus 3 over 6n cubed plus 1 divided by, and then we're going to divide it by this one, 1 over n. Okay, well, keep, change, flip. Think of your simple fractions. This is the limit as n approaches infinity of 4n cubed plus 3n over 6n cubed plus 1. And I don't know how technical your teacher gets, but as you can see, the degrees are the same. Therefore, this is going to be 4/6. In other words, it is greater than 0, and that satisfies this condition. The limit was greater than 0. We know this series diverges, so then this will diverge. So then we say, then the series, and you have to get super technical, 4n squared plus 3 over 6n cubed plus 1 diverges by LCT. Okay? So again, the way this works, limit comparison test. whenever you have something like this, okay, I do mathematics every single day. This is literally my job. So I'm going to answer Marilyn's question because she was asking this. So we always find the comparison by dividing all the variables and leaving out the constants. To be honest, that's what I would always do. People always suggest, or teachers will say, get rid of the noise, okay? And that's always, with problems like this, and the way we kind of identify that we're using limit comparison tests is typically you have like a nice quadratic or polynomial or quadratic, or in this case, a cubic, but you have a polynomial on the top and bottom. So limit comparison test is perfect for these, okay? And the idea is that, okay, this diverges, and when you divide the two, you're basically like finding when you divide it, you think of it like you're finding the ratio, and they behave pretty closely. Even though it's 4/6, it's not that big of a number, but the ratio between these terms and these terms are pretty close together. So because this is divergent, so is the other one. Okay, direct comparison is something very similar. Okay, but direct comparison is a little more difficult. Maybe I should pull up some problems. Are we here for direct comparison tests, guys, or should we stick to integrals? Okay, let's do another one. So we're going to do limit comparison tests, but let's talk about, maybe I can do direct comparison tests too, but this one gets really hard, okay? So I got rid of all these things. I did all the noise. This diverges, all right? Now, we have to... yeah, I agree. Integrals are more fun, but I'm going to do one more for Maryland just because a lot of students are covering series, and I feel like I should just do a whole live and a whole video on this. So with these types of problems, if we're doing comparison tests, once again, we already know this diverges. So this is the one that we want to compare it to. Now, this diverges. So what we want to do is, don't forget, our b sub n was 1 over n. Our a sub n was 4n squared plus 3 over 6n cubed plus 1. After this, guys, we're going back to integrals, okay? Because this diverges, or the series diverges, we need this to be less than or equal to this one. Now, why do we want that to be the case? Because if this diverges, I kind of want to draw a picture, okay? This will diverge. This is a 1 over n. Let's just say, for example, think of it like a picture. And if it's less than this one, meaning that it's going to be, this will be above it. If this is divergent, think about it, it's going to blow up. Well, this one will follow it as well. So if this blows up, so will the other. So every time you know that this one diverges, it has to be less than that. If this happened to converge, then it has to be the other way around because it needs to basically stop it from diverging. Okay? So I'm going to do this one, Maryland. If you have more questions, feel free to DM me or, comment on my videos, and then I'll make videos about that because obviously these are important. But in this case, again, you have to make this comparison. You have to show that this is true. So I'm going to multiply the 6n cubed plus 1 to the other side, multiply the n to the other side, and that gives me 6n cubed plus 1 is less than or equal to, multiply this n to the other side, and we have 4n cubed plus 3n. Okay? So let's just say, for example, oh my gosh, so we have to subtract this. We have to subtract the 4n cubed. This is where things get hard, and this is why comparison tests are a pain in the ass. I always do it as my last resort, but you have to show that this is true. So I guess what we can do is we'll have 2n cubed, I guess minus 3n is less than or equal to negative 1. So what I did is I brought the 3n to the other side to less than 1. And I don't think this is true. So the problem with this is with direct comparison tests, yes, we found that this is divergent. This has to be less than that, but I don't think this is going to be true. I feel like this is going to be false. So we can't even use direct comparison test. So hopefully, and again, I'm going to go back to the integrals, but with direct comparison tests, once you find what you want to compare it to, then you have to show that this is, since this is divergent, you have to show that this is less than this one. I think what we should have done is perhaps compared it to 1 over n, just like n cubed or 6n cubed, for example, because this one will converge by p series. And because this is convergent, it's stopping it from diverging. Okay? Okay. Problem 156. Marilyn, again, if you have more questions, please DM me. I will be more than happy to help. But guys, I want to continue with the integrals. And someone was just asking problem 156 on here. Yeah, we're not doing that one today, but I hope you're having fun. Okay, Marilyn, message me, send me a DM, or if you have questions, or get on Discord if you have that, and we can do that. Okay, thanks. Yeah, 156. Good luck with that, guys. I hope you're having fun with that. I want to go back to the integrals, okay? Just because I know a lot of people like to have fun with those. So here we go. Oh, this one was a pain in the... No, I'm not doing this one because I just know a lot of people are gonna be so annoyed with that. Actually, why not? I guess it's good to do these things. 9x squared plus 6x plus 5 dx. Yeah, I think it's good for A-level maths. It's definitely for a calculus. I wouldn't see it as like if you're trying to, do your A-level maths paper, I wouldn't bet on that. I would definitely, work on the study material that you typically do. Yeah. Hold on. Okay. Let's do this, guys. What do we do here? Someone said partial fraction. Okay. I mean, can we do partial fraction? Think about it. If we were to factor this out, can we even factor this out? 3x plus 1 plus 5. But that doesn't work, Rodrigo, because 3x plus 1, and then you said 3x plus 5, I think. That's 9x squared plus 16x plus 5. This is a 6x. So that's the issue, right, guys? If you cannot factor, there's something called what you can do slide and divide. Well, in this case, again, you can't, because if you do 9 times 5, that's 45. Well, multiplies to 45 and adds to 6. I can't think of a value. This is Calc 1, technically like Calc 2. So unfortunately, guys, for these problems, we have to resort to something else. And that is, someone said u-sub. I want you to think about this. Technically, u-sub could work, but if u is equal to 9x squared plus 6x plus 5, it's always good to write these down. Because look what happens. We get 18x plus 6 dx. Doesn't necessarily cancel out the x plus 1, that's kind of like the whole point, okay? So you can do it. There is a way to use something called the pun integral. So we're going to have to kind of find the best thing to do here. But someone already seems to have found it, which is exactly what we're going to do in a second, okay? So someone mentioned that we need to complete the square. And someone said 3x plus 1 times 3x plus 1 plus 4. Okay. So someone found a way to rewrite this. And that's kind of like the same way. Someone said 3x plus 1 times 3x plus 1 plus 4. Now let's just double check that this is correct. Well, this will be 3x times 3x. This is 9x squared plus 3x plus 3x plus 1 plus 4. You guys, 9x squared plus 6x plus 5. That is exactly what we have to do. Okay. Notice that it's 3x plus 1 times 3x plus 1. In other words, this is x plus 1 over 3x plus 1 squared plus 4. Technically, it is 4, but I'm going to write it as 2 squared. Now, the reason why I'm doing this, okay, is because I'm already setting myself up to use trig substitution. And the way trig substitution works is on the bottom, first of all, you can't factor it out. So we rewrote this as a perfect square plus some constant. And whenever you have the variable, the 3x plus 1 squared, plus the constant squared, then we have to resort to our beautiful, gorgeous right triangles. Always. And constant or variable squared plus the constant squared. Variable squared plus the constant squared. That means we're going to use tangent. And what I mean by that is tangent is opposite over adjacent. So my opposite will be this term, 3x plus 1. My adjacent is going to be 2. I highly suggest you kind of work these out because these are really, really fun once you kind of know exactly how to do it. Okay? So tangent, or actually if we use Pythagorean theorem, I hope you trust me that this is equal to root 3x plus 1 squared plus 2 squared. I highly recommend that you kind of work that out on your own. Because now, again, if we're doing trig sub, can we use a different pen? And let's use pink. Okay. So we're going to say oops. There you go. Okay. So we're using tangent, like I mentioned. Tangent theta is equal to 3x plus 1 over 2. So I'm going to multiply the 2 to the other side and get 2. Tan theta is equal to 3x plus 1. Now, some students can already take the differential from here. Some people like to separate the x by itself. So that's what I'm going to do. I'm going to divide the 1 to the other side. So subtract. 2 tan theta minus 1 is equal to 3x. So I'll get 2/3 tan theta minus 1/3 is equal to x. That's going to prove really helpful for us. Okay. Now we can take our differential. So we're going to take the derivative. The derivative of this is 2/3 secant squared theta minus 0. So we have our d theta, and that is equal to the derivative of x, which is our dx. Guys, this is exactly what we're going to use for the dx right here. And then now what we got to find is we got to find something that represents this. Well, we kind of have it in the hypotenuse. So we're going to use a hypotenuse and another side that doesn't have a constant. So I'm going to use secant because it's hypotenuse over adjacent. So I'll do secant theta is equal to all this stuff. 3x plus 1 squared plus 2 squared all over 2. If I bring the 2 to the other side, I get 2 secant theta is equal to everything here. 3x plus 1 squared plus 4. But it doesn't have a squared. So I'm going to square both sides. So 2 secant theta squared is equal to, this is what we need. Guys, I told you, this is super annoying. And I mentioned, like, I don't know if I want to do this. That's on the bottom there. Okay, let me just rip this up because we need to kind of refer to it. Okay, because now we need to start rewriting this integral in terms of theta. So we're going to do integral. And then we have x. Well, we know what x is. It's this term over here. So we have 2/3 tan theta minus 1, but then we have plus 1. And that should be a 1/3. My bad. That should be a 1/3. I almost put minus 1. All over, this entire value we established is 2 secant theta squared. Let me square it and get 4 secant squared theta. And then times our differential, which is this, 2/3 secant squared theta d theta. Whoop, that was pretty gnarly. That was nasty. But here we go, guys. This is kind of nice. Why? Because this cancels out. That's actually not bad, right? Let me just kind of simplify these things. So this will become 2/3 tan theta, and then this is negative 1/3 plus 3/3. So that's plus 2/3 all over 4 times 2, just 2/3 d theta. So let's, oh my gosh. Okay, let's just, what should we do? I guess we can cancel. This becomes a 1. This becomes a 2, right? And then this is a 2 times 3, which is 6. I'm just going to write this down a little more. 2/3 tan theta plus 2/3 over 6 d theta. And guys, we'll be almost done. I'm going to take out the 1/6 and the 2/3. So this is 1/6 times 2/3 integral of tan theta plus 1. Let me put the parentheses here to please those people that always yell at me about that. Okay, so this is 1. This is 3. Oh, 1/9. So we have 1/9 integral of tan theta plus 1. Guys, do we know the integral of tan theta? I hope we do. The integral of tan theta, let's put this on top, is equal to, we have 1/9, and then the integral of tan theta is actually natural log absolute value of secant theta plus the integral of 1, which is going to be theta plus our cheese. Whew! Let's go. Okay, now we're basically done, but we need to rewrite this back in terms of x. Well, we know secant theta. Secant theta is this entire thing over here. Okay, that's what we're going to write in here. So we'll do 1/9 natural log of root 3x plus 1 squared plus 2 squared all over 2. And then we have plus 1/9 because I distributed the 1/9 to the theta. Well, theta, we have to go back over here. Since tan theta is equal to this, theta is equal to tan inverse of 3x plus 1 over 2. And that's exactly what we're going to plug in here, guys. So we're going to have plus 1/9 tan inverse 3x plus 1 over 2. Whew. Wait. Absolute value closes here. Don't forget your plus cheese. And we are officially done, guys. I told y'all. This one was so annoying. Okay, someone was asking what pens. It's just acrylic pens. And I'm using like this black sketch pad. If you guys are ever wondering what I'm using, you guys can go on the link in my bio. And if you scroll down, it says like my gear. Then you'll be able to like, you'll get a link and it shows like all the stuff I use, like my blackboard and all that stuff. Yeah, it's nice, but super long. So TrigSub can be really annoying. Okay, enough with TrigSub for today. I think we got a few more problems. So let's do integral. Geez, what was that? Okay, integral. Where's everyone from, by the way? I live in Washington, where it's always raining. I hardly see the sun. So I'm curious where you are from. I do have a YouTube channel, so I don't do stuff like this. I'm not a big fan of like just doing lectures or like talking about stuff. Honestly, people like Black Pen, Red Pen does a great job. Professor Leonard, there's 3 Blue 1 Brown. They are doing their thing, and I don't know what I want to do with the YouTube channel. I'm almost at 100K subs through shorts, but I want to do like just wait. I think by the end of the week, I want to do like weekly problems that I found interesting, that I found in the wild, whether people, talk to them, mention them through the comments, or I saw like a nice video. So yeah, I don't do much of those things, but South Africa, wow, Arizona, Cali, I was from California, Iowa, wow, Mexico City, that's awesome. Bienvenido. Yeah. Arizona, always, the sun's always out, Florida. Anyway, this problem, what should we do? I have a 2x there. I don't like it. Saudi Arabia, welcome. Ecuador, oh, bienvenido. What do we do with this 2x? Rodrigo came in. Yeah, I need to do what I do on TikTok, but I don't know. We'll see. I agree. Honestly, it's just like you're filming vertical and then you have to turn it to horizontal. It's like a whole thing. Moscow, nice. Anyone from Berlin or Germany? I'll be there in a month, and I'm going to do a lot of integration stuff out there. Calculus pilgrimage, if you will. Guys, don't forget, this one right here is a double angle formula. And sine of 2x is equal to 2 sine x cosine x. That's it. It's identifying that right there. Because now you have integral of cosine squared x, and you rewrite this as times 2 sine x cosine x. Now, the reason why we did this is because we already just have x as an input. Okay, the cap Stevens, thank you. I'm going to continue doing that. I have to. It just needs to be done. Sine x, cosine x, everything now is in terms of x. It's not a 2x. The input value is just x. That's what we want to keep, okay? So from here, what we could do is take out the constant, okay? Factor that out. Yeah, you never use integrals, but come on, man. Who doesn't love an integral? Okay, so we're going to do sine x times, well, we have a cosine times cosine. That is cosine cubed x dx. And think about what happens next. Gosh. Yeah, you don't use integration ever, but I mean, think about the feeling of when you integrate and you write stuff. Like, what beauty do you, I mean, it's just incredible. We're going to do the next step, but while we do that, I do want to mention that there's a nice website called dailyintegral.com. It's not loading on my page for whatever reason. But anyway, dailyintegral.com. I highly suggest you guys go there and practice your integrals every single day. Someone said u-sub. Yes, absolutely. U-sub will work. And that's exactly what we want to do. Because I see a cosine cubed and we don't like to deal with that. Dailyintegral.com, that's right. So we want to do u-sub, and let's use a different color. How about this like neon green? So we do u is equal to cosine x. And the reason for that is because it's like to the power of 3. So we definitely, want to use that as our u-sub, For that reason, typically because it's a power, but also because the derivative of cosine is negative sine, and we have a sine right there. So du is negative sine x dx. I personally like to move this to the other side, and we account for our differential, which is right there. Okay, so what do we have? Let's move this up here. We have the 2 that was on the outside, integral sine x. The cosine now became the u, so we have u cubed. And then we have our differential, which is du over negative sine x. And that's what we wanted, guys, because the signs cancel out. So this negative could go on the outside, and we'll have negative 2, integral of u cubed du. Look how nicely that turns. It's a simple power rule. Negative 2, u to the power of 4 over 4. Let's not forget our plus cheese. And now we can just simplify. Well, I'm going to distribute the negative 2 and simplify with the 4. Got to know your fractions. This becomes a 1, then this becomes a 2. So I have negative 1/2, and now instead of u, it's cosine, because remember your u value was cosine. So cosine to the power of 4x plus your cheese, and you are officially done. That's it, my friends. Okay, someone said an improper integral. Let's do it. Yeah, let's talk about an improper integral. Actually, maybe, perhaps, and I could be wrong. But let's practice an improper integral. Okay, and let's talk about what that actually means. So, what happens when you have the integral from 0 to infinity? I think 0, no. It's going to be negative 2 of 1 over x squared plus 4x, and then hang on guys, plus 13. I think this will work. Well, Joe, you're in the right place. Okay, improper integral. So what does this look like? We have a function, and we're integrating from negative 2 to infinity. So you're taking the integral from negative 2 to infinity. You're finding the area underneath the curve from negative 2 all the way to infinity. But we can't do that. Technically, we can just plug in infinity, but the math, you know, that's a 13, my bad. The law says, you know, all the mathematicians will tell me you need to do a limit as b approaches infinity, and then you can do your limit. So you'll have limit from negative 2, and you have b on here, because technically we can't just plug in infinity. Taking the limit is essentially the proper term to use. But to be honest, if you kept the infinity there, which I typically do in my videos, it's no harm, no foul. Who the fuck cares? You have free will. You can do what you want. Okay. So once again, what we have here is something that we can't necessarily factor out. I can't think of two numbers that multiply to 13 and add to 4. So we need to complete the square. And it's one of the things that I truly hate, because everyone learns it differently. So the way I learned completing the square is taking this term. So we're going to take the x squared plus 4x, and we're going to take our b term, divide it by 2, and then square it. So b term, which is the 4, divided by 2 and square it. That gives you 4. So we're going to introduce a 4. We still have the plus 13, but because you introduced a 4, you need to subtract the 4, because you want to balance out the equation. If you notice, like if these canceled out, I can just do this. We have the same function, x squared plus 4x plus 13. But doing so gives us this factor right here, which is a perfect square. This turns into x plus 2 squared. This turns into the limit, as b approaches infinity, from negative 2 to b of 1 over, check this out, chat, x plus 2 squared plus, and then we just need to simplify this. Good night, Rodrigo. Have fun. Adios. See you soon. 13 minus 4 is going to be 9 dx. And guys, now we're prepped for a trig substitution, okay? This is a simple arctan integral. It shows up almost everywhere. If you're going to be an engineer, if you're going to learn about Fourier series, about Laplace transforms, if you're going to take any calculus course in higher level math, this integral is what just shows up all the time. The arctan is so essential. I mean, it's beautiful. And the way it just works out is gorgeous. Let me show you why, okay? Well, we have trig sub because we have some variable, x plus 2, it's part of the variable, squared plus 9. Let me rewrite this. So you can visualize what I'm going with. We're going to turn this into x plus 2 squared plus 3 squared. We like having this because x plus 2 squared plus 3 squared, I mean, it reminds me of Pythagorean theorem. So guys, we're going to draw out our beautiful, gorgeous, amazing right triangles. That was not that nice. So just bear with me. Okay. And whenever you have the variable squared, so x plus 2 is part of the variable, plus the constant squared, we're going to turn it into tangent. We're going to use tangent, meaning the opposite over adjacent. The opposite will be the variable, so x plus 2, and the adjacent will be your 3. Now, why do I use that? Think about Pythagorean theorem. 3 squared plus x plus 2 squared is equal to c squared. Well, if I take the square root, then I have 3 squared plus x plus 2 squared is equal to c. That's my hypotenuse, and that's what I have here. 3 squared plus x plus 2 squared. All right, no harm there. So what do we do here? Now we use our trig sub. So remember, I kept mentioning we're going to use tangent because of the setup right here. So we're going to say that tan theta is equal to x plus 2 over 3, opposite over adjacent. We move the 3 to the other side. 3 tan theta is equal to x plus 2. Some people like to have the x by itself, so we'll satisfy those people in the crowd there, and then make it negative 3 tan theta minus 2 is equal to x. Okay, why not just factor out the 3 squared? You totally can. Some teachers will actually say you need to factor out the 3 squared to make this a 1, and it makes your life a lot easier. Totally fine. You totally can. This is the way I like to do it, and I always suggest when you're doing integrals, it's kind of fun to see other people solve it because you're able to just kind of, see the tweaks and the way people are thinking. To be honest, it's beautiful when you see other people solving problems because it's not like you're doing it, and that's the beauty of math. We're going to get the same answer, but the approach is everything. Just imagine, you're driving home and some people like to go right just because they like the scenic view. Some people will go just straight and we all end up in the same location. I don't know. Everyone has different ways of doing their problems. So, I don't know what pens these are. I just got them on Amazon, but they're grabby acrylic pens. Yeah. Okay, so moving on to here, we're going to take the derivative. So we'll get 3 secant squared theta d theta is equal to our dx. Guys, this is our differential. This is going to prove helpful for this. Now we need an expression for this entire thing because we're turning our entire integral in terms of theta. Well, we have it right here in the hypotenuse. So I'm going to use a hypotenuse, and another side that's not a variable, I'm going to use the adjacent. Hypotenuse, adjacent. Hypotenuse, adjacent. That's secant. So secant theta is equal to hypotenuse, 3 squared plus x plus 2 squared all over 3. Move the 3 to the other side. We get 3 secant theta is equal to all this, root 3 squared plus x plus 2 squared. But then let's not forget, we don't want the square root, so we're going to square everything. Make it in 9 secant squared theta is equal to 3 squared plus x plus 2 squared. Okay. This isn't going to fit, as always. Hassan, you're funny, dude. Yeah, we'll do that later. Maybe we'll do like a video about proof. The formula for the Pythagorean theorem, a squared plus b squared is equal to c squared. Okay? All right, guys. I think we have everything. Oh, we need to change our bounds. That's kind of like the whole thing. Okay? So what do we have? So remember, our bounds were -2. So when we wrote when x is equal to -2, we're going to go over here. We're going to put -2 there. Okay, so we have 3 tan theta minus 2 is equal to -2. Okay, cancel these out. We get 3 tan theta is equal to 0. Tan theta is equal to 0. What value of theta makes it 0? Well, theta is equal to 0. That's perfect. And when x is equal to b, this is why I don't like to do the infinity part. I'm just going to follow this one over here. I'm just going to plug in b into this and get that tan theta is equal to b plus 2 over 3. And then so theta is equal to the tan inverse of b plus 2 over 3. Super annoying. This is why I don't like putting the b. I just like putting it infinity. But we have to follow the rules, guys. Okay. Okay, this will be my last problem because I am at 2%. So I'm just going to go ahead and do this real quick, guys. So we still have the limit as b approaches infinity. For the integral, well, the lower bound was 0. So we have 0. The upper bound was tan inverse of b plus 2 over 3. And again, just so you know, guys, I mean, there's shortcuts to this. A lot of people can easily see this and know the answer. But the whole point is to work it out. That's the whole goal of these lives. Okay? So we will do, oh, we're going back over here. So we have 1 over this entire thing. So 1 over this entire thing we established was 9 secant squared. Because remember, that's 3 squared plus x plus 2 squared. That's exactly what we have here. It's just switched. It's commutative. So we have 9 secant squared theta. And then we go over here times our differential dx. Our dx was this, 3 secant squared theta d theta. 3 secant squared theta d theta. Aha! Look what cancels out. The secant squareds, the secant squareds. This becomes a 1, and then this bottom one becomes a 3. So what we really have, guys, is the limit as b approaches infinity from 0 to tan inverse of b over 2, or b plus 2, my bad, over 3 of just 1/3 d theta. And again, this goes with an integral that's going to become an arctangent. Okay, I talk about this a lot in Book of Integrals and Book of Marvelous Integrals. Whoops, I almost move my iPod there. Okay, my tripod. Okay, so now let's go ahead and just take the integral of this. Well, this is just 1/3. It's a constant, so it's just 1/3 theta. But unfortunately, guys, we still have the limit as b approaches infinity. If I didn't write the limit, I know people will go crazy. So 1/3, we still have from 0 to tan inverse of b plus 2 over 3. And now we just implement the first fundamental theorem of calculus. Guys, this is our final problem. So if you want to keep seeing these things, I should probably go live once a week. But also, don't forget to follow. Just please. I think that support is the best. We're almost at 100K on YouTube. I mean, guys, and if you want to support, I have Book of Marvelous Integrals, Book of Integrals. I'm coming up with Book of Evil Scribbles. So, yeah, good times. But keep following and comment. Let me know what you guys want to see. So we have this. This became a 0, again, because I plugged in the 1/3. And then when I plug in the 0 for the lower bound, this just became 0. So now we're just dealing with this. Now, imagine I have 1/3 tan inverse. I'm plugging in infinity now. Now, again, this is so, how would you say? I wouldn't say illegal, but frowned upon. The math nerds get really crazy about it. This is infinity because it's infinity plus 2 over 3. Bro, that's just infinity. Because you have a really large number plus 2 divided by 3. That's still a large number. So we have 1/3 tan inverse of infinity. And I mentioned that you should know how tan inverse looks like. Tan inverse has 2 horizontal asymptotes. One at pi over 2 and one at negative pi over 2. And the function just goes like this. So what happens is we approach infinity. Well, we approach pi over 2. And that's exactly what we're going to put here. Our answer is 1/3 times pi over 2. In other words, pi over 6. And if you want to get really crazy, this is 1 over pi times the series from 1 to infinity over 1 over n squared. Honestly, I was just messing with you guys. That's just the Basel problem. It doesn't matter. When you see a pi squared of pi over 6, you definitely just want to do that. Oh my God. Sine x over x using Taylor series. Yeah, I don't know. Guys, this has been fun. So fun. I had a great time. I'm going to try to do this at least like once a week. I hope you guys enjoyed it too. I hope you learned something. I hope it motivates you to, get a pen of your own and just scribble away. That's math, baby. Whether it's integrals, whether it's any specific math problem, that's how you do it. You just write stuff down. You just get down and dirty, Before I leave, I'm going to answer any last minute questions people might have. Glad you enjoyed it. What am I using? This is just a black sketch pad. I just got it off Amazon. Okay. And I've been playing around with like different notepads, and this one kind of worked. And I'm using just like acrylic pens. Yeah. Again, you can go to the link in my bio, and you go down and you look for my gear. And on there, you'll see like a lot of the books that I have, you know, derivatives, limits, integrals specifically. This is like the most popular one. But yeah, you can go to the link in my bio. But if you go to my gear, it shows like the list of stuff that I like to cover. I'm noticing that people truly want to know, like, I guess what I'm using. So I just wanted to mention that. Yeah, these are acrylic pens, or at least that's what the description said. It says color flow. I don't know. Yeah, these are what I used. Yeah, I've been kind of messing around. Like I was doing like first I got like markers and like it didn't quite work. As you can see, like it doesn't even write. It just kind of erases. This is supposed to be pink, but on the black, it just doesn't work. So I went with acrylic pens. Yeah, and then, you know, if I'm on my chalkboard, it kind of mimics the chalkboard. I don't know if you guys see my videos, but it mimics the chalkboard there. So I really wanted to kind of just kind of mimic that same idea, the same feel, you know? And it's sort of fun. I mean, who doesn't want to just get crazy with this? Maybe I should just put these away. Yeah, guys, look. Let's just admire what we did. Let's admire what we did before we leave, okay? So I left you guys with my little signature. This is literally my signature. All that. We did all this. All this, and more. Oh my gosh, how cool. It's kind of exciting when you actually see it. Oh, this was just something else for a video, another video that I was doing. But yeah, guys, I'm so gonna do this. I'm gonna try to do this once a week. I'm just gonna hop on. And even if you feel like you are, you didn't catch the entire thing, I will post the replay. I think on YouTube, typically I can upload it. But I think TikTok now allows me to do, I think we're now allowed to do 1 hour uploads or something like that. So yeah. All right, I'm going to head out, guys. But once again, if you wanted, someone asked again, where'd I get this black notebook? If you go to my link in my bio and go to my gear, there's like a list of things. Again, I get commission off that technically. Because it's a link that I'm sharing. But if you don't care to do that, literally just copy like the product name and then just go on your own and just get it yourself. I don't want you guys to think that I'm trying to like, you know, profit off this or something. I just want you guys to truly enjoy the stuff. I mean, people are asking. All right, guys, I'll see you guys in the next one. If you have any questions or if you have any comments that you want to like, you know, add value to that, you know, put it on the comments in one of my videos. I typically do respond and I'll save the comments and I'll go with that. So yeah, follow me here on TikTok. You can follow me on Instagram. I'm also on YouTube. So yeah, it's all Matt Scribbles. Follow me wherever on Instagram. Can I not write my name? On Instagram, I post like some pictures of like math content and some videos that you'll basically see here. TikTok is a little more free, so I'll post longer videos. And in YouTube, still trying to figure that out. But, you know, you can see the uploads there. Yeah, guys, this was fun. I truly enjoyed it. I hope you guys have a wonderful time. Batman, Laplace transform, I did some videos. But it's funny, not many people are interested in it. But, yeah. But I'll try to make a video on that. Yeah, make sure you guys comment, follow. I'll see you guys later. Love you guys. This was fun. See ya.